Welcome to All About Logarithms in 32 minutes with a practice problem set in the description below. Now, what is a logarithm exactly? Well, a logarithm is just a mathematical tool to calculate the exponent of something. And all logarithms are going to look something like log base a of b is equal to c, where a is something called our base, b is our arguments, and c is our power or exponents. And really at its core, a logarithm is just another way to rephrase the exponential structure. So this entire thing over here is just the same as a to the power of c is equal to b. Or in more general terms, the base to the power of the exponent gives you the arguments. And logarithms are only used, so they're only used when c here, our exponents, is unknown. Now, a really funny way that I like to remember the structure of logarithms is to think of the entire thing as sort of a snail of sorts, where c, our exponent, sort of wraps around and sticks itself in between a and b, our argument, shifts all the way over to the other side, which leaves us with a to the power of c is equal to b. But really, I encourage you to find a method or a way of remembering things that works best for you, because as long as you remember that the base to the power of the exponent gives you the arguments, then everything should be fine, regardless of which method or way you choose to remember it. Okay, so let's try our first example now. So say we were given the equation log base 2 of 8 is equal to some unknown variable x, and we want to find the value of x without using a calculator, because if you had one in your hand, you can just punch in log base 2 of 8 and it'll spit out the answer. But we're trying to do this manually. So first, I'd like to encourage you to pause the video and see if you can solve it yourself. Okay, so firstly, what I'd like to do is convert this logarithm into its exponential form. And the reason why I'm doing that is to sort of clarify things and see what's really going on. So in order to do that, I'm going to use that snail method that I was talking about before, where the x shifts over to the left-hand side and the 8 moves over to the right-hand side. So really, this logarithm can be rewritten as 2 to the power of x is equal to 8. And now from here, we can notice that 8 really breaks down into 2 times 2 times 2, so 2 times itself sort of 3 times. So this entire thing is the same as 2 to the x is equal to 2 to the power of 3. And whenever you have two exponents where the bases are the same, then we also know that the powers must also be the same. So thus we can conclude that x is 3. Okay, now, so suppose that instead of given a question in its logarithmic form, we're given one in its exponential form. So maybe something like 5 to the power of x is equal to 75, and we want to find the value of x, but this time perhaps with a calculator, because the numbers don't seem so nice this time around. So as usual, I'd like to encourage you to pause this video, take a bit of time, and see if you can solve this question yourself. Okay, so the first thing that I'd normally do when faced with such a problem is to test out some values of x to see if I can get the equation to validate itself. But unfortunately, no integer value of x seems to get this equation to be true. Or in other words, 75 is not a perfect power of 5. But that's okay. That's completely fine, because we can use the other methods that we've learned to find the value of x. And the one that I'm talking about specifically is to get this exponential sort of equation into its logarithmic form. And how I'm going to do that is to use the reverse snail method, so snake over the x to the right-hand side, and move the arguments back over to the left-hand side. And so now we know the placements of these numbers, so we can go ahead and write it as log base 5 of 75 is equal to x. Okay, so things look a lot cleaner now, and we have x's on one side and numbers on the other. And it turns out that after plugging into your calculator log base 5 of 75, you get x as the value of approximately 2.68. And you can round this number to however many decimal places that you need. So there you go. Part 2, Special Logarithms. So at some point in time, you may have come across the expression ln of x, or what we call the natural logarithm. And don't be afraid if it seems initially quite alien to you, as all it's suggesting is that it's a regular logarithm, but with a special base of e, where e is defined to be Euler's number. So let me write that down, Euler's number. And to give a quick recap on what Euler's number is, it's basically an irrational number, which is approximately 2.718, just like pi or the square root of 2. And when it's used as a base of a logarithm, it implies that it is the natural logarithm. So ln of something is just a quicker and usually more efficient way of rewriting the expression log base e of something. And the key thing about the natural logarithm is that the same rules which apply to the normal logarithms also apply to it as well. It's just a special sort of logarithm with a constant defined base rather than some arbitrary number that you can plug into there. So it's really not that special. All you need to know is that it's a abbreviated version of rewriting log base e of x. Part 3, Logarithmic Identities. Now, the first identity we're going to be looking at is called the exponent identity. So, exponent identity. And basically what this suggests is that any logarithm of base a and argument b to the power of n can be rewritten as n times the logarithm with base a and argument b. And this identity is very useful for simplifying complicated logarithmic expressions and for isolating for variables, which we will do later on. But just for some key notes, the exponent n, in order for this identity to work, must only be applied to our argument b. It can't be applied to the entire logarithm, like something like this. As if this were to happen, then the identity isn't satisfied, so you can't use it in this case. And an example of this identity in action would be if we're given log base 2 of 5, and let's say the power here is 3. Well, we can rewrite this entire thing as 3 times log base 2 of 5. So it's going to look something like this. So the next identity we're going to be looking at is the multiplicative identity. So multiplicative identity. And this one basically suggests that if you have a logarithm base a of some x times some y, you can break this down as that same logarithm, base a, of x plus log base a of y. So you're basically decomposing this sort of product over here and rewriting it as two components of a sum. And an example of this would be if you were to have log base, say, 3 of 4 times 6, you could break this down as log base 3 of 4 plus log base 3 of 6. Now, similarly with the multiplicative identity, we have the division identity. So, division identity. And this one suggests an idea that's very similar. So, say you were given a logarithm base a of some quotient with the numerator as x and the denominator as y. Well, this entire thing can be decomposed into log base a of the numerator x minus log base a of the denominator y. And just to help you visualize it, say you were given, I don't know, an example such as log base 3 of 5 over 7 or something. Well, you can rewrite this as log base 3 of 5 minus log base 3 of 7. So next up in our list of logarithmic identities, we have something called the change of base identity. So change of base. And unlike the previous two identities, this one is sort of different in the sense that it doesn't follow the same structure of decomposing a product or a quotient into separate components. But regardless, it's still a very, very useful identity to have in your toolkit and will help you in multiple different problem-solving situations. So just as the name sort of suggests, if you're given a logarithm with a base of a and an argument of b, and you'd like to change the base of this logarithm into another value, so let's call that x, well then there's actually a really nice and systematic way of doing this. And the first step would be to create a quotient, where in the numerator you have a logarithm with a base of x, so you're implementing that new base that you want to sort of punch in, and the argument of this logarithm is going to be the same as the arguments in your original logarithm. So that's going to be b. And in your denominator, you are going to have log base x, so that new base you want to put in. But the difference here now is that the argument of this bottom logarithm will be the base of your original logarithm. So that's going to be log base x of a. And there you have it, a systematic way of changing the base of a logarithm into something else. And just to make a quick comment on, this identity in general, well, your new base, which is x in this case, could be literally anything that you want, provided that it's not something silly like a complex number, or in some cases even a negative number. So other than those special cases, this identity is very flexible. And just to help you visualize this a bit better, let's try an example. So say we have log base 5 of 9, and we want to change this into base 10. Well, just like we've done up there, we're going to create a quotient where in the numerator we have log base 10 of 9, and in the denominator we have log base 10 of 5. Now, the last identity that we're going to be covering today is called the reciprocal identity. So, reciprocal identity. And the thing with this identity is that it's practically a special subcase of the more general change of base identity. And it sort of suggests that whenever you have a logarithm of base a and argument b, its reciprocal will always be log base b of a. So notice here how the bases and arguments of the logarithm are essentially switching places. So the base of this logarithm is becoming the arguments of the other, and the argument of this logarithm is becoming the base of its reciprocal. So this sort of special change of base only occurs when you are taking the reciprocal of any logarithmic sort of expression, and its inverse also applies. So say you start off with 1 over log base 2 of 3, well, that can be rewritten as log base 3 of 2. So it works either way. All right, so now that we've mastered our logarithmic identities, I think it's time to put them to some good use. Okay, so here I've written for you a very standard logarithm problem where we want to find the value of x. And, as usual, just take some time to pause this video and see if you can solve it first before I explain it to you. Okay, so the first thing I notice about this problem is that the bases of these two logarithms are the same, which means that, potentially there will be no need to do any base manipulations or changes of bases in the future. So that's good news for us. But also, I see that these two logarithms are separated. So they're not together. And usually that's not really a good thing because when we want to solve for logarithms, we want them to be as compact as possible for them to be as simplified as possible. So can we think of a way to combine these two logarithms? Well, if you guessed the multiplicative identity, or rather its inverse, then you are correct. We can rewrite this entire thing as log base 2 of x times x minus 2, all in square brackets, which is equal to 3. And an interesting thing about single logarithms is that now we can rewrite the thing in its exponential form to really, get a more simplified understanding of things. So let's go ahead and do that. We have the base to the power of the exponent, so 2 to the power of 3, is going to give us our argument. So x times x minus 2. And from the looks of things have already gotten so much simpler. And when we simplify things even further, well, we see that we're left with a quadratic. And to solve quadratics, well, you put everything in its standard form, so you move everything to one side, and then you either factor or use the quadratic formula. But in this case, it seems like factoring is easiest, and after working with it a bit, you'll notice that the two numbers are x minus 4 and x plus 2. So this lends itself to two solutions. So two solutions. Either x minus 4 is equal to 0, so x is 4, or x plus 2 is equal to 0, or x is negative 2. But not all of these solutions might work. Because the thing with logarithms is that there's always going to be something called extraneous solutions, or solutions that aren't going to be satisfied when you plug them back into the original logarithmic equation. So in order to make sure that none of these two solutions are extraneous, we need to put them back in there to see what it'll turn that original equation into. So let's, label these solutions 1 and 2, and let's start with solution 1. So when we plug, x is equal to 4 back into our original equation, we have log base 2 of 4 plus log base 2 of 4 minus 2. And this turns out to be equal to 2 plus 1, which is 3. So this equation we know for sure is satisfied. But what about this other guy over here, x is equal to negative 2? Well, when we try that, x is equal to negative 2, and plug that in, we get log base 2 of negative 2 plus log base 2 of negative 2 plus 2. But there's a bit of a problem here. Can you spot it? Yeah, it's the fact that this guy here is negative, and this, when it simplifies, will give you 0. And why is this an issue? Well, if whenever you have a negative in a logarithm, you can't really find an exponent that'll make a base turn into a negative number, right? Because what this is suggesting is that 2 to the power of x is going to be negative 2. But is there any number x which will give you negative 2? Turns out no. So that means that this equation over here, so this guy over here, is extraneous. So therefore, we need to reject it. It's not one of our final solutions. But this guy over here, x is equal to 4, does work. So therefore, we have one solution, x is equal to 4. Okay, so let's try one more of these problems. Now here we have another one of these logarithmic equations where we want to find the value of x. So first, I'd encourage you to pause this video and take your time to try this on your own before checking your answer with mine. Alright, so the first thing that I notice about this problem here is that there is a lot of business going on in the center of this logarithm. So perhaps we can simplify that first before we get into the nitty-gritty stuff. And one thing we could try is to automatically go for the division identity and decompose this quotient, but that might get slightly messy. So what I'm gonna do is to focus in on this expression over here, 1 over log base x of 5. And we can see that this is actually just a reciprocal identity. So this can be rewritten as log base 5 of x. But there's another one of those terms up here. So what does that mean? Well, we can have log base 2 of log base 5 of x times log base 5 of x. And all of this is going to be equal to 3. And from here, this all here is going to be the same as log base 5 of x squared. So ultimately, we're left with log base 2 of log base 5 of x squared, which is equal to 3. And from here, we can use that exponent identity to bring down this exponent over here. So this is going to leave us with 2 times log base 2 of log base 5 of x. So things have definitely gotten slightly simpler here. And when we move this 2 to the other side, we're going to be left with, okay, you know what, let's go all the way up here. So we're going to be left with log base 2 of log base 5 of x is equal to 3 over 2. So we're very close to getting this entire thing to simplify down into one logarithm. But there's one more step that we need to do. And notice here that since we have a logarithm encased in another logarithm, what we can do is rewrite this entire thing as its exponential form. So I am going to say that 2 to the power of 3 over 2 is equal to log base 5 of x, because remember that the argument is just the base to the power of the exponent. So we're left with this. And from here, well, we can do that exact same operation again. We can do it twice. And that's going to leave us with 5 to the power, okay, this is probably going to get a bit messy, but 5 to the power of 2 to the power of 3 over 2, which is equal to x. So here we have our final answer of x, which is 5 to the power of 2 to the power of 3 over 2. But if you'd like to be slightly more concise with this, you can rewrite this as 5 to the power of the square root of 8, or if you'd like, 5 to the power of 2 times the square root of 2. And that is our final answer. And from here, I'd encourage you also to check for extraneous solutions and to see if this is really a solution that we can accept as being, well, one of the actual solutions to this equation. Part 4, the logarithmic function. Alright, so this part of the video will be dedicated to analyzing and interpreting the logarithmic function. But first of all, what really is this function? Well, it's just going to be something of the form y is equal to a times log base b of x minus h plus k, where y, b, and x are all essential components of this function. So without them, the function can't exist, while the constants a, h, and k are merely there to give transformations to the function, just as you would transform something like a parabola or an exponential or something along the lines of that. Now, some very important information that you should know about this logarithmic function is that, one, it's the inverse of the exponential function. So inverse of the exponential function. And basically what this means is that whatever input or output the exponential function possesses, the logarithmic function will simply undo that or turn it around. It's kind of like canceling it off. And this sort of makes sense because a logarithm, by definition, is the opposite of exponentiation. So whenever you are raising something to a power, the opposite of that would be taking the logarithm of that. So that's one way of thinking about this idea intuitively. But if we want to show that, through a mathematical proof, we can write down the utmost essential components of the logarithmic function. And from here, in order to find its inverse, we are going to interchange the placements of x and y. So that leads us to x is equal to log base b of y. And from here, we can use the idea that the base to the power of the exponent gives us the arguments. So y is equal to b to the power of x, and we have our exponential function. So indeed, we see that the logarithmic function is the exponential function's inverse. So that's very important. And another key thing about this function is that it has a vertical asymptote at x is equal to h. So it's going to have a point that the function never reaches or never sort of contacts at the vertical line x is equal to h. And this will be a very useful idea when we're graphing this function. So these are the two most, sort of essential components of the logarithmic function. All right, so now let's discuss some of the possible transformations that can be applied to the logarithmic function. So first we have a, which is the vertical compression / stretch factor, and it determines how much the function is stretched or compressed in the vertical direction. However, it also has a secondary role, which is determining whether it's reflected in the x-axis or not. And when a is positive or greater than 0, there is no reflection in the x-axis. But when a is less than 0, there is a reflection. Now the next constant is h, and this is the horizontal shift factor. And this one's kind of funny because it's placed within the logarithmic function, as in it's affected by the log itself. And so everything within that sort of category is going to have the opposite effect as its sign. So when h is negative, the entire function gets shifted to the right, but when h is positive, it gets shifted to the left. And finally, we have k, which is the vertical shift factor, and it determines whether the function moves up or down. And this one, since it's outside of the function, doesn't have sort of that opposite, effect to it. So when it's negative, the function gets shifted down, but when it's positive, it gets shifted up. Now let's try an example of this. So say we were given the task of describing the transformations of this function, as well as graphing it in the Cartesian plane. Now let's start off with transformations. First, there is a vertical stretch by a factor of 2, as indicated by this coefficient here. We also have a horizontal translation, 1 unit to the right, as indicated by this expression over here. And this transformation is found inside the function, which means that it's going to be the opposite of its sign. So since this h value over here is negative, we're going to be shifting it to the right. And finally, we have a vertical translation 3 units up, as suggested by our k value over here, which is 3. So these are our transformations. Now moving on to graphing this function, let's first start by creating a table of values, where we'll have x on one side and y on the other. And we are going to be plugging in x values, which are perfect powers of 2 minus 1. And that's because our base is 2, and whatever our x value is going to be is a perfect power of 2 minus 1 because of our h value. So for x, we can have 3, 5, and 9. And we can go on, but I believe that 3 points should suffice for this. And for our y values, when x is 3, we're going to get 2 times log base 2 of 3 minus 1 plus 3, which should give us 5. And when x is 5, we have 2 times log base 2 of 5 minus 1 plus 3, which should give us 7. And finally, when x is 9, we get 2 times log base 2 of 9 minus 1 plus 5, which turns out to be 11. And from here, we can draw our Cartesian plane. And I'm only going to draw quadrant 1 because all our points are positive. And remember that logarithmic functions have a vertical asymptote at the vertical line x is equal to h. And in this case, h is 1. So the vertical asymptote will be at x is equal to 1. And so we can draw that in there. And when we connect everything, we're going to get something that looks like this, though not necessarily drawn to scale. And just keep in mind that our function never crosses the line x is equal to 1. So it will get very close to, but not quite contact, our vertical asymptote. And there we have it, the complete transformed graph of the function f of x is equal to 2 times log base 2 of x minus 1 plus 3. And we are officially done. So thank you very much for completing this video with me until the very end. I hope that this has helped you develop a sense of confidence with logarithms. Make sure, as always, to check out that free practice problem set that I've attached in the description of this video. And until then, see you next time, and good luck on your mathematical journey.